when you have resistors in series, you know what to do. The R equivalent is R1 plus R2 plus R3. And when you have resistors in parallel, 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. In other words, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of all the other resistors, right? That's for parallel in, yeah.
For the in series, can you do the same thing where it's like the sum of the product?
No, in series it's just like 1 over. So in series, resistance equivalent in series is R1 plus R2 plus R3, etc. So if you have identical, is that what you got?
Just capacitance.
Oh yeah, I will come to that right. So if you have identical resistors, what is the R equivalent for identical resistors? If each one is R, it's going to be N times R for identical resistors. Now in parallel combination, if you have R equivalent in parallel, it is 1 over R equivalent in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. Now if you have identical resistors in parallel, 1 over R equivalent in parallel for identical resistors, it will be 1 over R plus 1 over R plus 1 over R. If there are n of them, it will be n over R. So what is R equivalent then? R over n. So let's say, for example, if I have 100 ohms resistors, 100 ohms, 100 ohms, 100 ohms, and there are 10 of those, what is the equivalent resistance? 1000. So 10 times 100 ohms. Now, if you have 100 ohms, 100 ohms, 100 ohms connected, 3 of them connected in parallel, it will be like 3 over R, 3 over 100. So this will be 100 over 3, which is 33.3. So if you have 300s connected, 300 ohms resistors connected in parallel, the equivalent resistance is this. Okay. So we're done, and then for parallel combinations, I gave you the shortcut for only 2 resistors. If you have only 2 resistors, you can find the equivalent resistance by taking product over sum. Now, we also saw the capacitors. In capacitors in series, when capacitors are connected in series, such as this, the R equivalent, no, the C equivalent of series capacitors. How do you find it out? 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3, etc. So just flip the thought from resistors to capacitors, it's just the opposite. So if you remember the resistors properly, as soon as you see capacitors, you just think again and say, alright, this is the other way around. And here also, when you have 2 capacitors in parallel only, product over sum works fine. Whereas when you have capacitors in parallel, the C equivalent is just equal to C1 plus C2 plus C3. This is in parallel. So just think again of the reverse process. Okay? Now, when capacitors are connected in series, what is common for all of them? The charge. Q is common. If you're not written down, write it down there. And when you connect capacitors in parallel, what is common?
Voltage.
The voltage is common. So capacitors connected in series, the Q here everywhere is going to be the same. Just like in resistors, when resistors are connected in series, the current flowing through all of them is the same. So just like that here, the Q here is the same as the Q here, is the same as the Q here. Whereas over here, the potential difference across all of them will be exactly the same. Now these clues will be useful when you're solving problems. When you have a situation, you have to solve it by using all these ideas. Alright, let us solve a problem now. Let us solve a problem using capacitors. Okay, so when you have capacitors connected to a power supply, what's going to happen is a load of charges will be delivered by the cell to charge all of these. But after waiting a little while, what will be the current in the circuit? Zero. After waiting for a while, the current will end up zero, because once all the capacitors are charged as is required, then there's no more charging current, because all these have built in a voltage which is equal to the power supply voltage. So let's do this. So I've given you the capacitances of all the capacitors, as you always do. First thing what you have to do is to find out if you can simplify the circuit. That's the first thing you should do. Now, what is the question here? The question here is to find the charges and potential differences across each capacitor. So if you need to find out all the charges and all the stuff that is a voltage that is stored across all the capacitors, what do you need to do? The first thing you should do is look for a way to simplify the circuit. Find out, can you detect something in series or something in parallel? That's what you do first. So as you can see here very clearly, these two are in series. So what do you do? Product over sum. Good, Jay. Product over sum. So 6 times 3 over 6 plus 3. Answer? 2. So basically this whole thing changes to 2. And now that 2 and that can very clearly be seen as parallel. So 2 and 6, 2 and 4 in parallel, add them up. 6. So now we have simplified the circuit to this. 12 volts. 3 microfarads and 6 here. That circuit has been simplified till here. Now what do you see? 6 and 3 are in series. So series, capacitors. In capacitors, series are just the opposite of, think always reverse. Like the moment you come to a series, then you say, all right, resistors in series, add them up, but capacitors in series the other way around. Product over sum. Okay? So 6 times 3 over 6 plus 3. These are not in parallel, these are in series. So 6 times 3 over 6 plus 3 is 2, so finally you have this. And just one capacitor, which is the equivalent capacitor of 2 microfarads. Is that clear so far?
Yes.
Good. Now, once you have discovered till here, the next thing you have to do is find out how much charge will sit on this, because this 2 microfarad is getting all the 12 volts. So how many coulombs is going to be here on these plates? 24. So 24 microcoulombs is sitting on the plates of this capacitor, which really does not exist. This is made up of 2 things. So it's 24 microcoulombs sitting on this, which means this cell has delivered how many coulombs? 24 microcoulombs. The cell has delivered 24 microcoulombs from here. So what do you think is the charge on this and on this?
4, 8, 9, 16.
How many will be here charge-wise? How much charge will be here? 24, 24? I told you to write it down also, right? That is correct. 24, 24. In all series capacitors, What is common is the charge. So when you know that this is delivered already 24 microcoulombs, where is it going to sit? It's going to sit here and here equally, not split. In series capacitors, the charge will be exactly the same. How many? Even if you have 100 capacitors, it's going to be the same. So 24 and 24. Now once you discovered this is 24, how many volts is going to be on that capacitor? So now you know one answer. This is 24 microcoulombs. So how many volts are sitting here? How do you find the voltage? Use Q is equal to CV. Get it? How many volts across this capacitor? 8. So you know the voltage there is 8 volts. Now look at this circuit carefully. Out of 12 volts, 8 volts is already dropped here. So how many volts will be dropped across these two ends? 4. The voltage that is across from here to here, this terminal to this terminal, should be 4. Which means this capacitor is receiving all the 4. So that is 4 volts. You see it now? You found out that 8 volts out of the 12 is gone. So the rest is 4. And this 4 must be sitting fully across this and across these two. So once you know this is 4 and you know the capacitance is 4 microfarads, how many coulombs? How many coulombs? 16 microcoulombs. Just use this equation. 16 microcoulombs. How much charge was sitting on all this together? On all this together. On all this together, 24 microcoulombs were sitting. Out of that, 16 is already here. So how much should be sitting on this section? 8. And that means how much should be sitting here and here? 8 each. 8 each. It's a very common mistake. The students write 4 and 4. No, they are in series. They should have the same. So again, 16 microcoulombs sitting on this leg. So on this leg, it should be the remainder of 24, which is 8. So therefore, 8 microcoulombs will be here and 8 microcoulombs will be here. Even if there are 10 capacitors like that, each one will get 8 microcoulombs. Because capacitors in series will acquire the same. Now once you know this is 8 microcoulombs and this is 6 microfarads, what's the voltage? Voltage is Q over C. Q over C. 1.33 volts. And how much is here? Because the whole thing is 4, it should be the remainder. Or 8 over 3, 2.67 volts. In this, therefore, we have found out everything. We found out the charge sitting on each one. We found out the voltage of that. Okay?
So you get it.
Now, what is going to be the difference? What is going to be the difference if I insert a resistor here? If I put a resistor there, what's going to be the difference? Zero. I just put a resistance over there. So what is going to be the consequence? What will be the, the voltages and the charges on the plates of these capacitors? What is the impact of this resistance on the circuit? The current will be? Which current? The charging current? There's no current?
After a while.
Well, after a while, there's no current anyway. But now I'm asking, what is that going to, like, what is the difference that can make to your problem?
So,
Yeah,
isn't it gonna slow down the
exactly.
technology?
It just slows down the process, nothing more. This will slow down the process because when you had no resistance here, there was hardly any resistance. Therefore, the initial current will be pretty high. Initial current trying to charge these up is going to be very high. And so all of these will get charged almost instantly. Almost instantly, they'll all get charged. But now that's not the case because you're controlling the current. So you don't get too much current flowing through this whole section. Therefore, the whole charging process will be delayed. So it'll be slowly doing it, but ultimately it will get 8 volts, 24 microcoulombs. It'll get all its share. Everything will be fine. Okay? Now if I put another resistor here, let's say 5 ohms. If I put another resistance here, 5 ohms, what is that going to do?
Slow the charging of the metal through.
You may actually remove this or keep it there itself, absolutely fine. What's going to be the will all the capacitors get to the same voltages and charges? That's my question. Yes.
Wouldn't the charge not go there because it would go to the path with least resistance?
So you're saying the charging current will come here and flow this way, not this way? Ultimately, how many volts is here? 4 volts? Isn't this receiving 4 volts? Then won't the current flow here? If a current is coming from here, the source must be from here. So the current is not going to stop. Right? Now think again. Think properly and tell me what is going to be the consequence. What is the effect of putting this one right there? What will be the potential difference across here and here and here? Yeah.
The difference will decrease because the resistor down there will take up a current,
This will take up a current, yes.
so it will take away from the total current that the
Is the current going to flow all the time?
Yeah.
Think.
Well, no, not until the capacitor.
Okay. So let me help you out here. Yes, there's a current going to flow here, right? Initially. And that's what is charging this up. What is supposed to be the current when everything is fully charged? Nothing? But how can this receive 4 volts and draw nothing? If this is drawing something, that current has to come from the source, which means this current is not going to stop. Yeah.
Will it just keep getting smaller and smaller?
The current? Until when?
It'll just keep getting smaller forever.
You're right. The current keeps getting smaller and smaller. So what exactly is the reason why the current is going down? And finally, the current over here is going to be 0 because the current is going to be 0. But what is happening in that process? Yes, we.
Do you mean like the voltage of the battery will also
Die?
die?
No. You are expecting the battery to be in good health. What is going to happen is this. This one previously got charged to 24 microcoulombs and developed 8 volts, right? But then now this current is still flowing. Therefore, this current will also continuously flow. And when this current flows, what's going to happen to this capacitor? It's going to get charged more and more. And what will happen to this voltage? It will keep increasing because you're not stopping this current because there's always a drainage here. So, and that drainage is going to slow down because this voltage is going to pick up from 8 to 9 to 10 to 11 to 11.9. It's going to pick up, continuously pick up as long as there's current. And this will actually grow to 12 volts. When this grows to 12 volts, then what's the potential difference here? 0, and here 0, and here 0, and that's when everything comes to halt. So no more current will flow. So what is going to be the charge on this capacitor? Because 12 volts should be here. So how many coulombs will this draw? 36. So once it reaches 36 microcoulombs over here, these will all get drained out. They will initially get charged, but they'll all get drained out. And finally, the potential difference across here will be 0, and here will be 0, here will be 0, 0. Only this will have 36 microcoulombs, and the potential difference here will be 12 volts, and everything comes to halt at that point.
So the other three capacitors.
Nothing will happen.
Zero charge.
They will all have nothing there because this has taken all of it. Because this was getting charged. Because to make this current flow, this was actually delivering the charges, and therefore this picked up the charges, got charged to the 12 volts. Once it picked up the 12 volts, the rest of the circuit gets nothing in terms of share, and so it stops over there. Yeah, a lot of things to look into when you're looking at a circuit, but anyway, don't worry about adding these resistances here and there. We will add them, and we'll see the consequence of adding resistances and all that slowly. So what's the point in having a capacitor? A capacitor's main purpose is to block DC and let AC pass through. A capacitor can let AC pass through because it can charge and discharge, charge and discharge. But it can't just keep charging because there's a time when it comes, like you got to stop. Once the voltage across the capacitor reaches the maximum possible, then there's no chance of charging anymore. So it will stop. And capacitors are used in multiple places. One of them is this, to filter off the AC part and keep the DC intact. Okay? Now, you've seen a voltage adapter, you know, the things that you plug into the wall? This one? What is this basically doing? What is this doing? This is getting plugged into where? Into the wall. What is coming through the wall? How many volts? 120 AC or DC? That is AC, alternating. And what comes here is DC. This is direct current because the current will only flow one direction. Whereas that socket provides current in alternating directions. That's why it's called AC. All these things are operating on AC. But to operate a television, it requires internally DC. Internally, DC is required. And so the first stage of a television is basically to take the 120 and take that and drop it or boost it up to all the required voltages that you need, because only an AC can be changed in terms of voltage, stepped up or stepped down by using transformers. So you can actually use transformers to step up or step down voltages. We'll see that in the next chapters. Transformers can be used to step up or step down. So in this adapter, the main component of this adapter is a transformer. You see that? That is a transformer. The main component is a transformer. So you can see the 120 is going straight there into this transformer, and then the output that comes out from here is passing through some diodes, and I'll explain all that right now. And you can see the main component sitting here. See this? What is that? What is that cylinder? That is a capacitor. This one. That's a capacitor. Of course, this one can change the voltages and all that, so you can select different voltages and you can switch the polarity as well. So there are multiple functions here, but main functions are transformer, diodes, and capacitor. Those are the main functions to make AC into DC. So let me draw this thing for you now. So this is 120 volts AC. What do you mean by AC? The voltage is going to be alternating. That's why it's called alternating current. The voltage is not the same. So you got two pins over there, right? In one pin will be more positive until here. And then the other pin will become positive. And then the first pin will become positive. So it's kind of flipping directions. So what's happening is the current keeps fluctuating in direction. So if I'm having an AC current flow through somewhere, if I have an AC current flow through a wire, in one wire the current will flow one direction for a short period of time and then reverses itself in the next. And how many cycles are going on here per second? What's the frequency of your AC outlet?
60.
60 hertz, correct. In India, in Britain, it is 50 hertz and 240 volts. Britain and India, they use 240 volts and 50 hertz. But US, Japan, they use 120 volts and 60 hertz. What is used in your place?
220.
Huh?
220 volts.
220? Yeah, which is the same as Indian.
I don't know about the hertz.
Then hertz must be 50, most probably. So, and there are some gadgets which can take both frequencies. There are some gadgets which can take both frequencies. Some can take only 60 hertz. So if it can take both 50 and 60, then you can use it wherever I go. So if I'm having an adapter, if I have like your phone charger, do you have a charger? Or any adapter? So when you have the transformer only transforms the voltage, but the signal still stays AC. And AC means it fluctuates between plus and minus and plus. Every cycle changes. So the time from here to here is 1/60 seconds, which is
0.0166.
0.0166, which means what is the time here from here to here? 0.008 something, right? The time from here to, that means for 0.008 seconds, it remains positive here. And for the next 0.008 seconds, it is negative. And then the next 0.008 seconds is positive, and like that, it flips. It's a very little time. So the current is electrons are kind of moving or oscillating basically. It's not a current that flows continuously, it's like vibrating.
How does it actually work?
Which one?
The AC, like how do the electrons just move back and forth?
You'll see that in the next chapters. When you do electromagnetism and all those things, we'll get to the right place where you will actually find out why it is fluctuating. Okay?
How do you solve this?
Huh?
You still need that. We'll get to that later, but
Yeah, I know. Very frequently this will be required. So anyway, so this is also fluctuating at the same frequency. How do you change from alternating to direct? Is by using these diodes. Those four things at the bottom, they are diodes. Now what's a diode? A diode is an electronic component. Its action is just like a valve. What's a valve? What's a bicycle valve?
That's something that you put
Air can go one way, but it can't go out. So the same way, a diode, which actually is, it looks like this. It looks like this with a ring here. If you look in carefully, you'll see that. The black cylindrical thing with the silver ring. Okay. This is basically a diode. This is plus and this minus. Symbolically, we write diode like this. This is a symbolic writing of diode. Like what is for resistance symbolically? That. For capacitance, it is that. For transformer, it is this. Symbols. But this is a symbol for a diode. This is plus and minus. What does this mean? It will let current flow this direction, but it cannot let current flow the other way. The mechanism of why it does so like this is done mostly in the electronics part. You can actually research and find out.
How do you spell diode?
Huh? Diode. Diode.
no question.
Alright, that's fine because you never know what a diode is, so
Yeah.
naturally you have to know everything. I'm just saying it. Some of you might have seen it earlier. So a diode is something that lets current one direction. See, there are 4 diodes used here, and this is how they're used. The circuitry is simple. And then the output is taken from here. That's your output. So let's look at this carefully. Okay, so you're connecting something to the output, right? You're connecting something to the output. So let's find out what happens when this is positive and this is negative. When this is positive, the current is going to go this way, right? Tell me which way it's going to go when it comes here. Will it go this way or that way? That way. And it will keep going like this. When it comes here, it will not go this way, but it will go out. So there's plus. And the minus is going to be taking up there and then comes here. Now what happens when the cycle changes? See, when this becomes positive, the current is going to go this way, it comes up, goes that way, and goes here. So this is plus again, whereas the minus is here. When the new cycle comes up again, same thing, current goes like this, out positive, negative. So you have changed this to that by using these diodes. So now what is going to happen is the output is going to look like this. The output is going to look like, so it's positive, negative. So this part comes through, no, this part here, not this one here. This one here comes out from here. Now what happens when the second half cycle comes through? The second half cycle is also flipped. So that one cycle is changed in this manner. The next cycle is also changed like that. So the output is going to look like this. What is going to be, this is the voltage and that is the time. Okay? So the output is going to look like this. Can you call it DC? Well, it's still fluctuating, so it is not straight away called a DC. But yes, the current is going in one direction only. Look at that. The current is going in one direction, but it is like fluctuating, which means the current is going and not going and again going and not, you know. So what we do right here is use a capacitor. There is a capacitor. Now what is a capacitor supposed to do? Here is a capacitor. When you put that capacitor here, what happens as soon as the capacitor receives that first pulse of voltage? The capacitor will also charge up. So the capacitor charges up to what voltage? To this voltage. So the capacitor charges up to that voltage in how much time? You know, this is 0.008 seconds, so that's almost like 0.004 seconds. In 0.004 seconds, the capacitor has already built up its charge. So the capacitor is building up the charge like that. Now what happens when the output goes down? So this output is going to look like this. What happens here? As soon as the voltage goes down to 0, will the capacitor completely discharge so quickly? No. Capacitors will take some time to discharge. That's what we're going to learn soon. The capacitor is going to take some time to discharge. And so what happens is the capacitor's voltage won't drop like that, steeply to 0. Instead, it will hold its charge. It is discharging, you can see that, it is discharging, but how much time is that from there? There's tiny, almost 0.008 seconds. So in 0.008 seconds, the next pulse comes in and fills up the capacitor again. So it fills up the capacitor again, and again discharges. Fills it again, discharges. Fills it again, discharges. Fills it again, discharges. So how is the output going to look like once the capacitor is put in? It looks like this. Like that. There will be some fluctuation. Now how do you get rid of that fluctuation also? Put another capacitor. Or a bigger capacitor. The capacitors mainly will smooth the output. Now if you put proper capacitors in there, the output can actually change from fluctuation to DC. And that is what comes out here. that is DC. And that is what is available here. So this is always going to be plus and this is always going to be minus. So if I connect anything to this, it's always going to be making current flow in one direction. So if I connect this to any object, the current is always going to flow from here to here. So what did you learn from this? Although we will learn this later on. Diodes, we're not going to touch that again probably. So at least you know what a diode is. It's actually an active component. It will behave depending on which way the current is entering. So the current is entering from here, it will let it go. If the current is entering from the opposite direction, it will block it. That's the basic idea. And by using these 4 diodes, the 4 diodes in this whole combination is called a rectifier. It rectifies AC to DC. It corrects AC to DC. It's called a rectifier. So that stage is a rectifier stage, which is the 4 diodes, and this is basically the filtering stages. And once it's properly filtered, you get the output very good. So if it's a very cheap adapter, you will get still bumpy output. And those bumps are called ripples. So if you look carefully at adapters, some good adapters will say how much ripple is present. That means basically defining the quality. Like what is the ripple factor? What percent of this output is ripples? They will say like 0.0 something, you know. So good manufacturers will always kind of say what are the ripple factors and all that. So it gives you an idea whether it's a good adapter or not. Some cheap adapters will have a lot of ripples. So if I use a cheap adapter to run a radio, the radio will like make a lot of noise. Because
How much is a lot of ripples?
oh, well, like this one is a lot of ripples, big ripples. Ripple is like the height, the amplitude sort of thing. So when you put one capacitor, see the ripple is kind of minimized in height. And now when you put very strong filters, you hardly see a ripple, which is like a very small percentage. You can't totally get rid of the ripples completely. So anyway, this is how you can get AC converted to DC and also AC changed to DC of different voltages. Because in a circuitry like a television, some sections will require 3 volts, some sections will require 6 volts, some will require 12 volts, some will require 500 volts. What is providing all that is mainly the transformer and these rectifiers. So once you rectify, now you cannot be just providing outputs for every section from the transformer. That is why what we do is, suppose I have 6 volts and I have a component that needs to be given 3.5 volts. What I do is I use the 6 volts, put a resistor, drop some voltage, and then connect it to the other one, right? So a resistor can be used to drop off some voltage. So you can actually divide the voltage from one section to the other section. So that's why you see a bunch of resistors in circuits. The main job of resistors is to reduce the currents or control the currents and to divide the voltage, both of them. We'll see voltage dividers and all that stuff. I think we've done it last year. Now, charging and discharging of capacitors. Charging of a capacitor and discharging of a capacitor. So let's talk about discharging of a capacitor first. So if I have and you're charging and discharging of capacitors through a resistor, all right? You're charging and discharging through a resistor. So we have a capacitor. And you have a power supply. and you have a resistor. That's a switch. This is for discharging capacitors only. Suppose I connect the switch, the capacitor is charged fully, right? If I connect the capacitor, capacitor is going to be charged fully, so it'll be plus plus, negative negative, and also there will be current flowing here. So if I'm going to apply a voltage, if I'm going to apply the maximum voltage, which is basically the EMF. So if I'm going to apply an EMF, this is going to charge up to the EMF. The voltage to which this one charges is E. And if the supply is this, we don't generally write the E. It's not necessary. You can write V as it is and go on. But you can say that E is the voltage to which this charges up fully, and then resistance R here is also going to get a current. It's going to get a current because you have a certain voltage applied and this is a resistance, so there will be a current flowing through the circuit, right? Now, when you disconnect this switch, all you have is this. When you disconnect the switch, I'm removing it so that you'll see it better. Alright, when I disconnect the switch, the EMF is gone. Now this capacitor will have a voltage across itself. And this resistor will have a voltage across itself. So what is happening to the capacitor from now on? Because I've disconnected it, this will make a current flow this way, right, through the resistor. There's a current flowing through the resistor in this direction. It's kind of reverse current. It's not a charging current, but a discharging current. It is not a charging current, but a discharging current. So this is a current that is discharging the capacitor and making the voltage go down. Now, if you can apply Kirchhoff's laws over here, the loop rule, you can say from here, if you go this direction, that's positive VC, and that is negative IR, correct? So the current is I, so that's positive VC minus IR is equal to 0. So what you see from here is VC is equal to IR. The VC is equal to, what is VC? Voltage across the capacitance. But you should understand one thing. This current, you can replace current in terms of charge. So if the charge across here is Q, suppose on the plates we have charge Q. How can you replace VC? What is VC equal to? Using the expression Q is equal to CV. What is VC in terms of the others? Yeah, Q over C. Capacitance is C, so I can write it as Q over C. The Q over C is equal to dQ over dt times R. I'm just doing it using differentials and all that. So the Q over C on the capacitor is equal to dQ over dt times R. But you know what? The dQ over dt is not a charging current. It's a discharging current. In other words, the more this flows, the Q is not going to increase but decrease. And since it's a decreasing current, we can insert a minus sign right there or here, wherever. The Q is going to drop. The voltage VC is going to drop. So I can insert a minus sign wherever. So it's minus Q over C. This is the reality. Minus Q over C is equal to dQ over dt times R. Now we just shuffle the Q's and the T's. Now R is a constant. C is a constant. The two variables are Q and T. So if you rearrange this, we can see minus dt over RC minus dt over RC is equal to dq over q. Is that okay? Is that okay from here? I'm leaving the dq straight there. I'm just only bringing the q down here and throwing all the rest to the other side. Now we're going to integrate this between the times 0 and t, and between charges. The initial charge was q naught, highest charge. And the final charge, let's call it q. We don't want a complete drain. We are actually, from 0 to a certain time, we want to know how much the charge is going to go from q naught to q. Okay? When it was 0 time, it had full charge q naught. But after passing, the time passes to some extent, that is what it is. Now, how do you integrate this? dt t minus t over RC, boundaries 0 to t, is equal to natural log of q, and the boundaries there are q naught to q. Now, working on that again, if I put t over here, then you get the same expression. Put 0 with 0, right? So finally you have minus t over RC is equal to, putting the limits, it's q minus natural log of q minus natural log of q naught, right? And now this can be also written as natural log q over q naught by using the product quotient rule. So log a over b is log a minus log b. And now this is a natural log. Therefore, if I bring that e up here, so e to the power of minus t over rc is equal to q over q naught. Therefore, q is equals to q naught times e to the power minus t over rc. This is the charge that is going to be left after this much time elapses. This is a charge, this is the original charge. And this is a charge that is going to be left after some time passes. Okay. Now plotting this on a graph, this is how the graph will look like. Q versus time. When time is 0, e to the power of minus 0. So what will be Q? So initially, you start with a full charge capacitor. And after some time passes, it's going to fall off exponentially. It's going to come down exponentially. So the discharging of a capacitor will look like that. Only when time is infinity, Q will be 0. Only when time becomes infinity, Q will be 0. So that's a discharge graph for a capacitor. Discharge graph for a capacitor. Actually, if you divide both sides by time, you can actually find out also another thing. The rate at which this charge is going to change, and the rate at which the charge changed earlier, that will tell you I is equals to I naught, e to the minus t over RC. So if you're plotting a graph of I, then you start with the current of I naught time. In fact, that I naught is going to be a reverse current, so it will be minus current. It's going to be like this. When you're charging it, it's going to be positive current. When you're discharging it, the current starts in the reverse direction. So actually it's going to be I naught, and it goes like that. And you can see from this graph as well. What is the slope of this line at this point? Positive or negative?
Negative.
Negative value. The slope of the Q time graph is going to be the I time graph. So this slope is negative maximum, negative maximum. And at this place the slope is lesser, value is lesser. And finally the slope becomes 0, it's supposed to be 0. Right? Questions? Yeah.
Why wouldn't it be into the negative t over RC over t?
Over T, where's the T?
Because you divided each side by t.
No, I didn't divide by T. Where? Oh, here?
Yeah.
Oh no, this T is, I mean like, I'm dividing both sides by T here, T and T. I'm not going to touch that one at all.
That's right.
Okay.
Get it? Q over T and Q over T.
It
just changes to I naught.
I understand what he's doing, but like mathematically, it's just I'm just trying to like wrap my head around it.
Yeah.
No, the time, this time is variable.
Yes.
Well, you can actually use the same time here, but you know this is totally a different factor. You don't have to bring in the T anyway. So in other words,
It's been wrapped.
Current is charges.
yeah, I'm trying to do it a shorter way. He's right. I'm trying to do a shorter way by just saying like divide. But truly what you're supposed to do is to differentiate this whole equation and then discover. So the minus sign will actually come. That is why it's coming out here.
Yeah.
Right. So that is the real way of doing it. He's right. So if you truly differentiate it with respect to time, the times minus 1 will come out. And that is what makes it a negative current. Okay. Yeah, I'm trying to just get the format of the equation and so you can understand this. Now in terms of voltage, if you use the equation Q is equal to CV and replace this with CV and CV naught, right? If you replace this with CV and CV naught, then you can knock off the two C's. So you have a new equation. The voltage across the capacitor is going to be changing according to this equation. So the format of the equation is exactly the same. So how is the voltage going to be changing? Voltage times, initially the voltage is high and then it falls off. Do you get it? So the voltage is going to change in that fashion, the charge is going to change in that same fashion. Current is going to be discharging current, and that's why it starts with the minus sign and goes off like that, because the current is going in the reverse direction. You can also derive an expression for charging a capacitor and get an expression for that. Derivations are not really important as far as you're concerned, but sometimes they may pop up something like that. But again, you're not doing the physics C. In physics C, this is definitely a question. When you're doing physics C, they'll ask you to derive the expression for charging of a capacitor or discharging of a capacitor, and you got to differentiate or integrate the same way. But since you're doing algebraic version, you don't require to know the details, but you don't need the equations. You need the equations. I can derive the other one if you want, but maybe I'll go straight into the expression. For charging of a capacitor, the equation is going to be Q. When you're charging a capacitor, it's Q is equal to Q naught. That's going to be the expression. We can derive it also the same way as we derived this one. Similarly, the current is going to also fluctuate like this. So how does this mean? This means the charge initially is 0 at time 0. When time is 0, the charge will be 0 to start with. And then the charge builds up like that and then reaches saturation. So this is a charging graph. And what is the initial current? Positive or negative? Positive. That's why the current graph It'll be like this. The current graph will go that way because this is positive slope, positive value. Less slope, less value. And this is Q naught. Okay? And the voltage also will go exactly like this. Voltage will go exactly that way. This is for charging of a capacitor. If you are keen on deriving it, I'll derive it next class.